Hello, today we're going to talk about measures of variability. So let's say Joe, Kyle, and Larry are on the same basketball team, and the number of points they scored in the first six games of the season is shown in the table below, as well as their averages. So if we look at this data, notice something kind of interesting is that all of them have the same average, right? But their data is very different, right? So I'm going to use this simple Greek letter mu for the average, right? He's got an average of 20, he's got an average of 20, and he's also got an average of 20, right? But what's different, right? Who seems more consistent? Well, you can see Joe is a lot more consistent. His points are always very close to 20. Kyle varies a little bit, and Larry's all over the place. He could score 3 points one game, 37 points the next. Now, again, it's not realistic that this would exactly happen, but it's making a point that in order to really get a bigger understanding of the data, we need more than just calculating the mean. We need to have something that can measure or quantify the variability. Now, in real life, most cases won't be this obvious, like comparing Joe to Larry, but you might look at different data sets and you might want to wonder which ones tend to vary more away from the mean. So one idea is one way we can start by doing that is let's look at their points at a different table here. And what I'm going to do is I'm going to take all their point values and I'm going to subtract them from the mean. So I'm going to pick, let's take this column right here, and I'm going to label it xi, because that's kind of a standard in statistics to call it each point in the data set as xi. And what I'm going to do here is really I'm going to calculate xi minus mu, or in other words, xi minus 20. So 20 minus 20 is 0, 21 minus 20 is 1, we got 0 and 0, then this gives you a negative 1. Okay, so we could do that for all of them, right? So if we look back at these, again, it's the same table, so I can subtract xi minus mu, which in this case is still 20, and I get negative 2 here, then I get 2, then I've got 5 right here, and then 4, then negative 2, then negative 7, right? Now let's do the same thing for the last one. We're going to do each value minus 20. Now 10 minus 20, now that's negative 10. We got a positive 10. We're going to get a 5. Let's see, 3 minus 20 is negative 17. 37 minus 20 is a positive 17. And then we got a negative 5. Okay, so you can look you can look from the tables and see this one has a lot more numbers that are varying. You see the red table. But to kind of summarize, what we can do is try to find an average of these. However, if I try to average these numbers just as they are now, when you average, you add them up and then you divide by the total number, meaning that if I add these all up, notice they're all going to add to 0, actually. Again, 1 plus negative 1 is 0. These ones, the negatives balance the positives. So the next step we could do, this is where the different types of measures of variability differ, but the easiest way is just take the absolute value, right? Let's just take the absolute value of xi minus mu, or each data set minus the average, and here we get 0, 1, 0, 0, 1, 0. And then, of course, over here, we get 2, 2, 5, 4, 2, 7. Again, this is absolute value. We're going to call it xi minus mu, means the data point minus the average. And then over here, again, all we're doing, taking absolute value is very easy. You can do it in your head. You just take away the negative if there's a negative, right? So that's that. So what we can do then is now we can average these. Now, this is a formula that we call the mean average deviation, or it stands for MAD. So the mean average deviation, the formula is you sum the absolute value of each data set minus mu, and then just divide by n, which is the total number. So in this case, the total number is there are 6 things. So we're going to add this together, 2, and then we're going to divide it by 6. So the MAD for Joe, or the mean average deviation, is about 0.3, repeating. And then, if we look at Kyle, if you add all these together, you could do it from a moment if you want, or use a calculator, you're going to get 22 over 6. That's going to give us, as a decimal, like 3.6 repeating. And then, if I add all these together, ooh, this is a lot more. But if you add them all together, you should get 64. And we take the 64 divided by 6. And that will give us 10.6 repeating. So now we have a specific quantity, right? This is the measure of variability called the mean average deviation. That tells you if you have a bigger mean average deviation, it means it varies more. And we can see that Larry's point values vary more than everybody else's, and Joe's points vary the least because that value, the number, is lower. Cool. So this one is pretty straightforward to calculate. Again, find the absolute value of the differences and then average those. Now, this equation was developed in like the 1700s that we know of finding a mean average deviation as a way of finding a measure of variability. Now, in the late 1800s, they developed a new measure called the variance, and the variance was used especially because it was helpful in relating to advanced statistics that uses calculus. The absolute value function is very hard to do calculus things with, but another way that you can turn something that's negative and turn it positive is to square it. And in more advanced mathematical operations, that ends up being a lot more useful when you have a smooth function that's differentiable when you square it. So let's look at how we would do that. So now I'm going to take each data value minus the mean, and I'm going to square it. Now this table becomes the same because 1 squared is 1, so squaring it is the same as the absolute value. If I go over here though, and I'm doing each data value minus the mean squared, now I get 2 squared is 4, 4, I get 25, 4 squared is 16, 2 squared is 4, 7 squared is 49, right? I'm going to do the same thing over there. Xi minus mu squared. Squaring 10, you get 100. And then 25. And then if I square 17, I get 289, actually. 289 squaring 5 gives me 25. Okay, but now we're just going to do the same thing. So the only step that was different between the variance and the mean average deviation is just instead of absolute value, we're squaring it. Now we're still taking an average. So let's write the formula here for the variance. Now the variance, they use this Greek symbol sigma squared, and we're talking a little bit why we call it sigma squared, but it's not part of the formula, just the variable itself for variance is sigma squared, is equal to the sum of xi minus x mu squared over n. Okay? Again, I'm using n for the total number in your data set. So let's do that now. We add this together, we got 2 out of 6. So the variance in this case is the same. The variance is like 0.3 repeating. Now for this one though, if we add all these together, we're going to get 102. 102 divided by 6 will give us a variance of 17. And then now if this one adds up to a lot, it actually adds up to 828. You can check that yourself if you want. If we divide that by 6, we're going to get a variance of 138. Okay. Now these numbers are a lot bigger, but they serve the same purpose. You see, a bigger variance means it varies more, where a smaller variance means it varies less. Again, the variance, it's just more helpful for some more advanced applications. But another thing that's more helpful, notice these numbers are very big, so they decided shortly after coming up with the variance to come up with a new thing that we call the standard deviation. Okay, so the standard deviation is simply the square root of the variance. So here's how the official equation will look. You see, standard deviation is just sigma equals square root of the sum of the data minus the mean squared over n. So now you see why variance is sigma squared and standard deviation is just the sigma, because you can see clearly the relationship is that the standard deviation is just the square root of the variance. So for us, since we already have these variances calculated, we can find the standard deviation. So let's do that. The standard deviation is simply the square root of this, and that will give us a standard deviation of about 0.57. I think we'll run to 0. It'll be 0.577. I'll use 2 decimals there. And then for this one, again, I'm just taking the square root of 17. Square root of 17 gives you about 4.123. And then I take the square root of 138. And that gives me about 11.747. Cool. So now we've found the standard deviation. Now, again, what do these do? The standard deviation, the variance, and the mean average deviation, they all do essentially the same thing. They give you a measure of how much you vary from the mean, right? Notice standard deviation has become the most popular for a few reasons. Now, people like it better than the variance because it's kind of a smaller number, right? You're not really varying on average by 138, but in this case, you could say, hey, his points tend to vary. A standard deviation from the mean is like 11.7. Again, mean average deviation seems probably just as good as standard deviation if you're new, but as you get into more advanced applications, there's a lot of neat results that come from using the standard deviation, specifically in things like a normal distribution. There's very nice patterns you see by analyzing a number of standard deviations away from the mean. But hopefully that helps with knowing how to calculate both the mean average deviation, the variance, and the standard deviation. Again, here's the formula for these two. And actually, let's give a summary of all three equations. So here's the mean average deviation, the variance, and the standard deviation. Again, the equations can look scary, but just remember the process. And specifically, you add up the absolute values, or you add up the squared version, and with standard deviation, you take a square root, right? Now, last thing I should mention, though, is that these formulas specifically are for the population. So if you have the entire data set, if you have the population, like for example, if an IXL problem just says, hey, here's the data, find the standard deviation, these are the equations used. Now, there is a separate equation, though, if you're finding a sample. So for example, if you have the data for like test scores for an entire school, but then you sample just 20 students and you want to find a variance and standard deviation from that sample, we use different notation. They use S squared and S for variance and standard deviation if we're talking about a sample. Now, mean average deviation doesn't change, but for the variance, we would say the sum of xi minus, we use the term x bar for the average of a sample. Instead of dividing by n, the total number, you divide by n minus 1, the sample number minus 1. Again, there's kind of more advanced reasons for why they do that. Again, if you're just doing a straightforward problem, hey, here's the data set, find the standard deviation, you're going to find this. But I wanted to introduce this equation just in case you do see that. If you're taking the variance or the standard deviation of a small sample, then you would just use those formulas.